An electron that has been accelerated from rest by a potential difference of 250 volts enters a region of magnetic field of strength 0.12 Tesla that is directed into the plane. The electron path is the quarter circle, shows that speed of the electron after acceleration is equal to. We can apply just law of conservation of energy. Work done on the electron, its charge multiplied by potential difference, and it is equal to the kinetic energy gained by a given electron, so it is equal to mv squared over 2. Hence v is the square root of 2ev over mass of an electron, and it is equal to square root of 2 times elementary charge. It's 1.6 times 10 to negative 19 times 250 and divided by 9.1 times 10 to negative 31, which is equal to 9.4 times 10 to the power of 6 meters per second to two significant figures as required. The next radius of the path is equal to a given value, so let's consider a second Newton's law. Net force vector in general is equal to ma. And what is force which acts on a given electron? It's a force that acts on a moving charge in a magnetic field. It's also called Lorentz force, and it is equal to charge, speed, and magnetic field strength, and its centripetal force. And acceleration is v squared over radius, since it's motion in a circle. And we can simplify, and hence radius is mv over eb, and it is equal to 9.1 times 10 to negative 31 times 9.4 times 10 to the power of 6 over elementary charge 1.6 times 10 to negative 19 and 0.12. It is oh no, it's here, magnetic field strength. And it is equal to 4.5 times 10 to negative 4 meters to two significant figures as required. And the next question, time the electron spent in the region of a magnetic field. And time, it's distance over speed. Distance, it's a quarter circle, 2 pi r over 4, and speed is in denominator, so it's pi r over 2v, which is equal to pi times 4.5 times 10 to negative 4 over 2 times 9.4 times 10 to the power of 6, which is equal to 7.5 times 10 to negative 11 seconds to two significant figures as required. And the next part of this question, the diagram below shows the momentum of the electron as it enters and leaves the magnetic field. The magnitude of the initial momentum and the final momentum is, and it is equal because it moves with constant speed in a circle. On the diagram above, draw an arrow to indicate the vector representing the change in momentum of the electron. Change in momentum, it's the final momentum minus the initial momentum, and it's the difference of two vectors. So we should apply the rule for vectors for the difference of two vectors. And to find the difference of two vectors, we connect endpoints and arrow is to final. So it's delta p. P final vector minus P initial vector. And it's the required vector. Show that the magnitude of the change in momentum is. Magnitude, it means we need just magnitude of this vector, and we can consider a given triangle which is a right angle triangle, and just applying a Pythagorean theorem, we can write that delta P is equal to square root of 8.6 times 10 to negative 24 squared plus 8.6 times 10 to negative 24 squared. And since it's an isosceles right angle triangle, we can just write that delta P is just 8.6 times 10 to negative 24 multiplied by square root of 2. And it is equal to 1.2 times 10 to negative 23 Newton seconds to two significant figures as required. The time the electron spends in the region of magnetic field is. Estimate the magnitude of the average force on the electron, and applying formulas that impulse F delta T is equal to change in momentum. The average force is delta P over delta T, and we need just 1.2 times 10 to negative 23 divided by time, which is 7.5 times 10 to negative 11, and it is equal to 1.6 times 10 to negative 13 newtons. And that's all for this question.